Hello friends, Uncle Lee here with a brief discussion on how to find the area bounded by two curves. As you can see in our example, we have the blue curve here, which in this particular case is going to be a function of x, and we have the red curve here, which again in this case is going to be a function of x. Later on, in some more advanced problems, if you will, we will look at some area bounded by curves that are functions of y, where x is a function of y. And then we'll also look at some area bounded by curves that are neither functions of x nor functions of y. This concept of area bounded by curves is one of the main applications of integration and one of the easiest topics that we will discuss with respect to integration. So let us begin by looking at the area bounded by these curves. Well, goodness gracious, it certainly doesn't look like this area is bounded. And it is not. There is an intersection point here at A, B, but if I look here, this particular area is not bounded. Now, the concept of unbounded area is something that we will talk about in Calculus 2, but we're going to keep our discussion simpler here since we're still in the realm of Calculus 1. But we have to some way or another bound this area. And we are going to bound this area simply by, hey, let's add another curve. Let's add this vertical line x equals d. Now you can see that this area is bounded. It cannot get away. It is bounded. It is bounded by the curve f of x, by the curve g of x, and this vertical line x equals d. So our problem then is to find this area. If you recall from our earlier discussion on how we developed the definite integral, we began by looking at rectangles. And we're going to develop this formula to find the area in a similar manner. When we're defining the definite integral, we began looking at rectangles where each rectangle had equal bases. And it's the same process here. We're going to create several rectangles, and each rectangle is going to have the same base of delta x. The only difference here is the bases are not lying on the x-axis as they were before. But other than that, it's the same principle. What we're going to do is keep getting smaller and smaller rectangles, smaller and smaller bases, therefore more and more rectangles, until we get so many that we're going to actually find the area, this yellow area here. The key here, and it was easier the last time, it was easier when we were defining the definite integral to find the height of each rectangle. The height of each rectangle was simply the function value at a particular x value in some interval. We would take any x, sometimes we'd do the right-hand x value for that interval, or the left-hand x value, or the midpoint. And then as we developed more and more rectangles and this idea of this limit, we can pick any x value. Same principle here. We can pick any x value to find our height, but the difference is now is the height. And that's the big question. What is the height of each rectangle? Well, this is the height of this rectangle, this is the height of this rectangle. How do I find the height of each rectangle? And I will tell you that for some students, they can see it right off the bat. For other students, it takes them a while to wrap their head around it, so we're just going to take it nice and easy. And we'll begin by a discussion. The height of this height is some vertical distance. It is some distance, vertical distance. This concept of vertical distance is going to be a big topic, or very useful when we start revolving things and finding volumes of solids, volumes of things when we rotate areas about particular lines. But here we're back to finding the vertical distance. The height of some vertical distance. For example, if I have this constant function y equals 5, and this constant function y equals negative 2, what is the vertical distance between these two lines, negative 5, or pardon me, 5 and negative 2? What is this vertical distance? It seems easy enough, and many of you would say, hey, that vertical distance is 7. And to you I would say, you are wrong. That vertical distance is not 7. That vertical distance is 5 minus negative 2, which just so happens to be 7, and I was just joking about the 7. But we need to start thinking about the daggone vertical distance as being the top minus the daggum bottom. Vertical distance, top minus daggum bottom, top minus daggum bottom, top minus daggum bottom. You need to think about that as being the vertical distance. The height is some vertical distance. For example, the top is 5, the bottom is negative 2, so this vertical distance is going to be 5, or the top, see if I have this here, it's going to be the top minus the daggum bottom, which in this case, it's going to be 5 minus negative 2, which is 7. Top minus daggum bottom. So let's go back to our problem now, where we needed to find the height of each of those rectangles. Or really, we just wanted to find the height of one rectangle. We just need the height of one rectangle. And like I said on the previous slides, the height, the vertical distance, is going to be the top minus the daggum bottom. And I purposely made g of x below the x-axis here. So g of x from about this point on is a negative, and over here is positive. But it doesn't matter. This vertical distance is still the top minus the daggum bottom. The height of the rectangle is the top minus the daggum bottom. And in this case, the top is f, and the bottom is g. So this height is going to be f minus g. And if I go back up here, yes, g is positive here. But this height isn't going to be that much. This height is going to be this positive f value, subtract this positive g value, and it's going to be that distance right there. And when g is over here is negative, it's going to be this positive f value, subtracting this negative g value, so that's what gives us this height of this rectangle. Top minus daggum bottom, top minus daggum bottom. So now the area is very easy. Similarly, as we did when we were finding definite intervals, the area of one rectangle is going to be the height times the base. The area of one rectangle is the height times the base, or the base times the height. The base in this case is delta x. The height in this case is f minus g. Height times the base is the height area of one rectangle. Well, we don't want the area of one rectangle. We want the area, we want all of those rectangles. So we want the shaded area. And the shaded area is going to be the sum of all of those skinny little rectangles. The height of all the rectangles. The base of all the rectangles. How many rectangles are we going to add up? We are going to add those rectangles up from this x value a to this x value d. So the shaded area is going to be the integral from a to d of f minus g of d of x. Let's do an example. Let's find the area bounded by the graphs of f of x equal to x plus 3 and g of x equal to x squared minus 3. The linear function x plus 3 is easy enough to graph. The quadratic function x squared minus 3 is easy enough to graph also. We want to find the area bounded by those two graphs. This is the only area that's bounded by those two graphs. This is the area bounded. Some teachers like to, sketch a rectangle, sketch a rectangle. I, on the other hand, would suggest to you just sketch one height of a little itty bitty skinny rectangle. Because all we really need to find is this vertical distance. And what is that vertical distance? What is any vertical distance? It's the top minus the dadgum bottom. The height, which is a vertical distance. And the top here is going to be this linear function x plus 3 f of x. And the bottom is going to be this quadratic function x squared minus 3. So the height is going to be f of x minus g of x. For this particular case, x plus 3 minus x squared minus 3 quantity. And so the area is simply going to be, and we want to take note here that these two curves, and this is going to be important when you go to do your assignments. You need to find out where those functions intersect at. I picked an easy example here, and it's easy to see that these functions are equal. It's easy to see that f of x is equal to g of x when x equals negative 2 and when x is equal to 3. Whoopsie, 2 up too high, sorry. Easy to see that f of x is equal to g of x when x is negative 2 and x is equal to 3. That's going to give us our lower limit and our upper limit for my integral. And it's simply going to be the integral, so this yellow area is simply going to be the integral from the lower limit, negative 2, to the upper limit, 3, of the top minus the dadgum bottom. So the shaded area, integral from negative 2 to 3, top minus dadgum bottom, d of x. I will allow you can either use the analytical version of the fundamental theorem to evaluate that or stick it in your calculator. This is what's going to be most important for you. Thank you.